Okay, good evening, everyone. Today we will continue our journey into neural networks by looking at optimization. However, before we jump into this optimization, there is something else I want us to just quickly look at. Last week, we did a bit on how we would define a model in PyTorch. So we essentially learned how we can use PyTorch to build models. And I didn't share my notebook, right? But I hope that everyone did take the opportunity, um, go back to, your the recording and go check the PyTorch website, right? And just see a few things there. But I'm going to share this notebook, the notebook that we did last week, um, immediately after this class. I did forget to do that. So remember last week we looked at all the different ways, the different concepts basically in PyTorch and what PyTorch gives to us. Gives to us data sets, data loaders. We talked about tensors. We talked about the dynamic computational graph, which is really what allows PyTorch to speed up the computation. And then we talked about autograd, which is automatic differentiation, the automatic calculation of gradients. That's autograd. Remember, all of this while we've been talking about training a model, whether it's a linear model, whether it's logistic, whether it is a decision tree, whether it's a support vector machine, or any of the other algorithms. It really always boils down to optimizing, right? And what's optimizing? You have a loss function. You calculate the loss based on the loss function or the cost function. The loss function and the cost function are more or less the same thing. It's just that the loss function defines the loss for a single data set, while the cost function defines the cost for a large set. So for the entire data set, that's what I mean. So, you know, um, when you are training a model, you want to minimize that loss. So you have to calculate the loss. And we figured out, we went through the basics of gradient descent, which is like the um, grandfather, like the foundational method in modern times of building or training models, right? So for you to train a model, you will first of all need to calculate the loss. Then most importantly, you need to calculate the gradients of the loss function. So you first of all have to define a function that is the gradient of the loss function. Basically, you have to do a derivative of the mathematical equation that the function is. You do that derivative. When you do that derivative, then that gives you the gradient of loss function. That gives you another function, right? Which you can then plug in the same variables to calculate the gradient. So when we are calculating the gradient, we're not actually um, differentiating numbers, right? We are rather um, kind of deriving a function, another function that is the derivative of the loss function. That function we derive, that is a gradient because that is what determines how steep, the loss is at that point. And we've also seen that the whole essence of minimizing the loss is to get to the minimum value. And at the minimum value, that's where the gradient is zero. So by minimizing the gradient, in other words, going down that gradient slope to where the gradient is zero, you have effectively, by the time you get to where the gradient is zero, you have effectively completed training the model, right? At the point where the gradient is zero, if you go beyond that, you cannot really go beyond that point, right? That's like the most that model can learn. So a key part of training neural network is getting the gradient at every point in time. And it is also one of the key problems because there are some functions that are difficult for you to obtain the gradient function of it or the derivative function of it. it becomes difficult. And because it becomes difficult, um, it's a challenging thing. So that's why you find that functions that are non-differentiable are not used in neural networks or in any algorithm for that matter, because you basically cannot train in a model that is built with that function. So that's the whole story around gradients. And that is why gradients are so important, or the gradient functions are so important. And this problem was solved the day when, well, it was solved, but it was made easy, for users like us in PyTorch when they, came up with this idea of autograd. So autograd basically means that PyTorch can look at a function that you have made and it can come up with the difference, the gradient of that function. And there are many ways it does that. For some of it, it just basically looks at the function and they are pre-made functions. For others, you look at a computational graph and so on. So um, that's what AutoGrad module does. So once you build a model using PyTorch's own built-in primitives, it will automatically obtain the gradient functions for each of those that you use to build it up. And when it is doing back propagation, remember propagation is just a chain rule, chaining the gradients backwards. From the loss function, you multiply all the gradients, and then at the end, you multiply that by the power of the signal that is coming in, which is the X. Okay. And that's it. So we'll look a little bit at AutoGrad, right? Before we go into optimization. We've talked about tensors, we've talked about modules. So what is AutoGrad? It's PyTorch's automatic differentiation engine, like I said. It's essentially an engine. So it uses a lot of different algorithms to figure out, what should be the gradient function for any function that you use. So whatever mathematical equations or functions you use in building your model, right? PyTorch is able to establish or figure out the gradient of that function and use that gradient of that function when it is doing back propagation. So it typically just tracks the operations, like I say, on the tensors. Remember, the tensor operations are converted into a computational graph. So that's what it does. It builds a computation graph automatically. Because it is building a computation graph as you are building the model, right? It is also able to reverse, you know, the computational graph. And, when it is doing the backprop, it's able to identify and use the gradient function. So why AutoGrad matters, it it helps you in that you don't need to manually define all your derivatives, right? All this while when we're doing our stuff, we would have to define a function and call it gradient. Then we'll have to do the gradient, even though it was easy because we're using gradient of simple linear equations, right? Which are pretty simple. Or when we did a gradient of the um, uh, binary cross entropy, which is what we use for logistic regression. Or you could even say categorical cross entropy. But there are some things that it becomes difficult to calculate gradients. We are going to look at some of those, when we're talking optimizations. So some of the activation functions, which I think I showed us some of them, and that was part of the task that was given to you when you are calculating swish, mish, ReLU, all of that. There are materials that I also provided for you to read and find out how these gradient functions are derived. But all of these are done under the hood by PyTorch using the AutoGrad module. So this enables the back propagation. It allows for gradient-based optimization, and it allows for deep neural networks because then you can stack any number of layers of neurons, and you don't need to worry about how back propagation is done because it automatically does the back propagation for you. So there is a backward function, right, which is defined not in your model, not in the NN.module, but in the optimizer, right? Sorry, the criterion class, which defines what kind of loss function you are using. because when you look at it, the is a loss function that determines the gradient, basically, because we are talking about gradient of a loss function. Okay. And then that gradient is taken and then it's also cascaded backwards through activation functions and all of that using the chain rule. So this backward function or method is defined in the criterion class that carries all the loss. Okay. So this backward method will calculate and compute the gradients of the output with respect to all the tensors, right? When you define that that tensor has requires gradient. So remember, the tensor is the basic unit of representation of numbers in PyTorch, right? You use tensor. A tensor is basically a representation of a number, 0 dimensional to n-dimensional, right? And you can define that that tensor, this particular tensor, requires gradient. In other words, it is part of the parameters that should be updated. It's only parameters that need to be updated that will require gradient, like the weight and the biases. Okay, but there are some other parameters, or I wouldn't say parameter, there are other tensors which are not parameters. So for example, the signal that comes in, right? The X values that come in do not require gradient because they are not parameters that you want to update. So for all tensors that have requires grad to be true, right? Those ones, gradient will be calculated for them and stored, right? The gradients are stored in the dot grad attribute of the tensor, okay? So with that, the computation graph can be discarded, right? After the single backward pass, and we now have gradients. Each parameter has gradients. The gradient will now be used by the optimizer to then update the value of the parameter. So you see that PyTorch has basically separated, it's kind of separation of concerns. It has separated the training loop, right? It has separated the calculation of gradients from the update of the parameters. And I showed that a little bit. So I'm just going to go to, um, I won't talk too much about AutoGrad, but let's just look at, you know, let's look at the PyTorch website and just look a little bit at their AutoGrad. So we'll go to documentations, PyTorch, and we can just go to the user guide. And in the user guide, you see at the bottom here, you will have all the main concepts. Um, PyTorch overview. So, well, there's a list here. Learn the basics. Right. So learn the basics. You have this. So we'll just go to AutoGrad, and then we can open up the Jupyter notebook. We had looked at all the others, right? Well, we skipped data sets and transforms. Data sets and data loaders are basically, the things that help you load data and clean it. Transform, like I said, is feature engineering, basically. So we're in AutoGrad, and let's just look a little bit at this. So I'm going to open the Google Colab. I'll just quickly look at. Okay, so you first of all notice that there is a touch.autograd. So touch.autograd is a PyTorch function that you know enables the differentiation. So when you're training the neural network, of course, backpropagation, and in backpropagation, you have the parameters which are adjusted according to the gradient. So let's look at a few things. If you have uh, just to show us how AutoGrad works, right? A simple one layer neural network with an input X, right? Which is a single tensor right? A single tensor that has 5 elements. Okay. So touch that one's 5. Then we have an expected output, which is also a single tensor that has 3 elements in it. So effectively, you have created a neural network that has 5 inputs and 3 outputs. Okay, 5 inputs and 3 outputs. So if you look at that, you then see that your 5 inputs and 3 outputs basically correspond to a weights matrix that is 5 times 3, basically. So we declare a weights matrix here, right? Touch dot random number. And remember, we always start weights with random numbers. And it has 5 by 3. So basically, this is like saying 5 inputs and 3 outputs. Okay. Um, and then the requires grad is true. So this is what we are saying, that any weight, any tensor that you want to do automatic differentiation on, or you want to apply the auto grad on, you have to specify requires grad. And you normally only use that for parameters. So in this case, you can see that the W and the B are the parameters of this neural network, right? While the X and the Y are not parameters. These are signals coming in. X is the value of, X coming in, and Y is the training targets that you want to train your network on. Okay. So you now define this. This is a very simple definition of the transfer function, right? Which is a math mole of X and W. That is basically X W plus B. This is the linear equation, which is a mathematical a matrix multiplication. So this is like saying there are 5 x's. So x1, x2, x3, x4, x5. And then the y, there are 3 y's, y1, y2, y3. Okay. So you're now doing x1, x2. Essentially, you are doing let me see if I can sketch it. So it's easy to visualize and map this maths. This is basic maths, right? But you can see that this essentially still maps to um it still maps to neural network and matrix representation. So you can see that X is um 5 inputs, right? Um so you can even represent it this way. Yeah, my sketch is not very neat. Okay. So and then this is this, right? So what we are saying effectively, you now have the weights. So this is the weights matrix. You see the matrix. It will have um you have X. This is the X matrix, which is the signal, right? And there are 5 values here, X1 all the way to X5. Okay. And then the weights, the columns will match the number here, while the rows will match the Y values, because you're going to have 3 Y values here, Y1, Y2, and Y3. Okay. So this matrix is going to be a 3 by 5 matrix. That's a weight matrix. And that's typically how it is. That's why you do a module of X versus W. Well, if you could also have it's even though one thing I want to say is that if you look at this structure, it doesn't exactly match this, but that's really what it is, right? 3 by 5. So even though this is giving us 5 rows and 3 columns, but essentially we know it's a dot product and it will give us the same results. So by the time you do this, you are going to come get back 3. So whatever values you have inside W, right? That is this, which is 5 by 3. It's a parameter, so it requires gradients. Then, oh, I forgot the part where you have to add it plus the bias. And the bias is, again, just three, which is B1, B2, B3, right? B1, B2, and B3. So this is the simple representation. This is a matrix representation. If I wanted to use a regular neural network representation, then you could also do it the same way, where you would have five neurons, okay, as at the input layer. And then you have three neurons, right, at the output layer. And then you have interconnection between these, right? So every neuron here is connected, right, to every neuron here. So you have five connected here. You also have five connected here, right? And this basically amounts to the same thing, right? And so on and so forth. So each neuron, the input will be connected to two others on the output, and so on. So this is a 3 by 5. So this weight matrix that you see here, right? This is the 3 by 5 weight matrix here. Okay. So that is just three different ways of viewing the same thing. It's all still the same thing. We're just viewing them in three different ways. So, but this is how PyTorch views it, right? This is the computational graph, right? When you are doing maximum of X times W plus B, it first of all does a graph. So a computational graph is basically, like the name implies, in this case, it's graph, not a chart, but a data structure called a graph data structure that is made up of, leaves and parents, nodes, and root. Okay. So the root is the loss. But to get to the loss first, you first of all calculate the function itself. So you have X times W. So X and W are the two elements that come in, right? The two operands. And the operator is the star, which is um the dot product, right? Then the result from that dot product is added to bias. So the result is also an operand, and the bias is an operand, and it comes in, and you have a sum. So it just sums the result from X times W with B. And then that goes, and that is Z, right? Which is the intermediate sum, or the um the um the weighted sum, basically. So this Z, right, is now, in this case now, because we do not have an activation function, right? We immediately just calculate the loss by doing a binary cross entropy with logits Z and Y. So we do a binary. So remember, binary cross entropy, it was one um 1 - y times log of y hat minus y, okay, plus, or rather, let's say the other way, it's y times log of y hat, okay, plus 1 - y times log of 1 - y hat, okay. So, but that is what is happening inside this function. So this will calculate using this function, and you get the loss. So that's the CE, right? The CE means cross entropy. It's taking the Z, which is the output from that layer, and the Y, which is your training data, and it calculates it, and that gives you the loss. So with this, you have a computational graph that calculates the loss, right? Now, in all of this entire graph, it's only these two that have been defined as parameter. That is, they are defined with requires grad to be true. So what it means is that when AutoGrad is doing the calculation, it is going to calculate gradients. You use gradient function to calculate gradients for W and B, but it will not calculate gradients for any of these other ones because they're not needed, right? So these are the two you need to optimize, of course. So you need to be able to compute the gradients of loss function with respect to those two variables. That's what I actually mean when I say gradient. It's actually a gradient of this loss function with respect to W and B. So we set requires grad to be true, which is what I said. Then like, well, one thing, yes, in PyTorch, you can set requires grad when you are creating the tensor, like it's done here, or you can set requires grad after the tensor has been created by just saying something like b dot requires grad, and then you pass the value of what it should be. True. So any function that you apply to this tensor, right, as you are constructing the computational graph, right, um, is an object of class function. So because the object, any function, it's an object of class function, it means that the object knows how to compute the function in the forward direction, but it also knows how to compute the derivative of this function in the backward direction, which is a gradient, right? In the backward propagation step. So a reference to the backward propagation function. So like what we did, every function has a gradient function defined for it. And if you are taking a built-in PyTorch function, that gradient function is automatically defined for you. But if you are creating a function by yourself of your own, you will have to define this gradient function itself. Okay. So let's look at that. I've run this bit of code which does all of this. So we have a computational graph for loss. If I actually come here to print that loss, which we just did, you will see that it tells you it's a tensor and it gives you the value of that tensor, but it also tells you something. You can see what it tells you, that the gradient function is binary cross entropy with logits backward. So in other words, there is already a built-in gradient function that comes with the cross entropy function, right? So because we have loss is a function that has been calculated from a binary cross entropy equation, it is automatically assigned this built-in PyTorch binary cross entropy with logit backward loss function. The other thing you can also do is, okay, let's compare, let's see a bunch of these other ones. Everything else, the X, Y, W, B, Z, right? So let's see what those ones look like. X, Y, W, B, Z, okay? So if you look at X was defined and requires grad was specified, right? As well, it wasn't specified. So the default value will be false. This is taking a bit of time because it's trying to calculate everything. But you can see that the first tensor here is X. It's just the ones, right? 5 ones, like we saw. The second tensor is Y. It's 3 zeros, right? We had defined Y as 3 zeros. Okay. Then we had defined the W and B as weights, okay, with this shape. So W has 5 rows and 3 columns. But you can see requires grad is true. We have defined it to require gradients. Then the second one, the other tensor, which is a B, right? We have defined it. So you can also see it's a tensor that has 3 elements, randomly selected. And you can see requires grad is also true because we defined it. Then you can see that the final value Z is also a tensor calculated by the weighted combination of this, but it also gets a gradient function defined for it, which means that, and what is the gradient function? Add backward. Because if you look at this computational graph, Z was obtained by an addition parameter. It was, sorry, addition operation. So an add operation is what gave rise to Z. So it will have a gradient function of backward add, which, you know, um, it knows how to do the necessary necessary differentiation or calculate the necessary gradients. So this is printing the loss function for Z, what I just did. So you can see the loss function, the gradient function for Z is add backward because add was used to obtain Z, and the gradient function for loss is binary cross entropy with logits backward because the loss was also calculated using the binary cross entropy function. And that's it. So with this now, PyTorch knows for every tensor how to do or what to do when doing the backward propagation. It knows what to do. So in this case, to optimize, when you now do loss.backward, right? Like I said, the loss has a function called backward. Loss is a criterion object, right? Um, it is also a tensor. Actually, it's a tensor that comes out of that calculation. So you can do backward on that tensor, right? And it will know how to do backwards because it knows the gradient function and it knows all the preceding loss knows this is the function that was used to calculate it. So it knows the gradient of it, which is the backward version of this. And then it also knows the elements that were combined, to create it. So it can also that um backward function knows how to still take this input and then calculate the gradient, right? And then it will send it backwards. So that's how it works. So if you now do this, you now see that when you do loss of backwards, it's going to essentially calculate gradients backwards for all of them. And you see that the weights, the gradients, the backward when it's done, the weight will still be stored in the tensor in an attribute called grad. So if you look at the grad of the weight tensor, you can see that it is the same three. This is because the gradient actually depends on the output, right? So for each of the y's, remember there are three y's, y1, y2, y3, right? Y1, y2, y3. So each of these y's will have its own. You see that all the y's, this is for y1, all the gradients are the same, 0.90929, 0.0929. And then for y2, all the y's, all the gradients are the same for all the weights that are connected to y2. And then for all the weights that are connected to y3, you can also see that all the gradients are the same. Then, of course, this is the bias gradient, and you can also see the same thing. There are three bias values, B1, B2, B3. B1 is connected to Y1, so it will also have the same gradient. B2 is connected to Y2, so it also has the same gradient and so on. So the next thing that you would do is you now take these gradient values and you would now update the actual parameters. If you were doing it manually, you would just do a learning rate times this, right? You would just do learning rate times this gradient and you subtract it from the original value, right? That is what we would do, and that's what we have been doing. But that learning rate times this is gradient descent algorithm, right? Gradient descent optimization. So what's um what you know PyTorch does is that it now delegates that thing to the optimizer or optimizer class, the optimizers, which we are going to talk about next. So if you are using a gradient, regular gradient descent optimizer, it will just take this gradient, multiply it by a learning rate, and then use it to reduce the weight or improve or update the weight. But if you are using a different kind of optimizer, maybe like stochastic gradient descent or mini batch gradient descent or adaptive moments estimator, and it will use that exact same formula. Formulas differ, right? So that's where optimizers come in. We'll go to that shortly. So, but the main thing to note is that you can only obtain the graph properties for the leaf nodes of the computational graphs, which have requires graph properties set to true. In other words, what we mean by leaf node is the tensors that are at the beginning, right? These are leaf nodes. Is a leaf node, B is a leaf node, W is a leaf node, and X. In other words, nodes in the computational graph that don't have anything, any child, right? They only have parents. This one has two. This is the parent, right? So these ones are, ordinary nodes or parent nodes, and then this is the root node, which is the parent of all of them. But these ones are leaf nodes, right? So you only have the grad calculated for these leaf nodes, but only the leaf nodes that have the requires grad set to true. So you see that it's only W and B that get their grads calculated, right? X and Y don't get their grads calculated. That's the main thing. Um, yeah, so that's just explaining how autograd works. So for all the other nodes in the graphs, the gradient will not be available, and you can only perform gradient calculations using backward once on a given graph for performance reasons. If you want to do several backward passes, like you want to do backwards multiple times, you have to put retain graph equals true when you are calling backward function. Otherwise, once backward function calls, it deletes the graph, it plays a computational graph because the computational graph is built on the forward propagation. So that on the backward propagation, that computational graph will be used to calculate the you know the different gradients. And after it is done, the graph will be cleared because the graph is quite quite heavyweight and it takes a bit of memory, right? So yeah, if like by default, all tensors have requires grad set to true to track the computational history and support gradient computation. But for situations where you do not want to do that, right? Maybe you just want to do only forward computation and you don't want to train, like you are just using PyTorch to do what we call inference. You're not planning to train the network, so you don't need to calculate any gradients. Then what you can just do is to set requires grad to be false. Or you can use touch.noGrad, right? In a touch.noGrad block like this one, no gradients will be calculated. Even if for some reason those parameters or those tensors were marked as requires grad to be true, right? Um, and that's because by default, all tensors, you know, once you have requires right true, their computational history will be tracked. So in this case, you can see that here they did two examples. In the first example, they did the same calculation of Z twice, but in the second one, they put it in a no grad block. So you can now see that in the first one, requires grad is automatically set to true, but in the second one, requires grad is set to false. So it will not calculate in this second case. And this is typically what you do for inference, where you don't want to train the model. If you're not planning to train the model, you're not really, you don't need gradients because you only need gradients for training. But gradients also take a bit of time. They incur computational costs and they also incur memory space cost. So you don't need to use gradients where not needed. The other way is to detach, right? Well, and this is one thing we find that detach it allows you to detach the tensor from its gradient. Okay, so in this case, we detached it. If you remember last time when we did a bit of some calculations, when I was trying to convert, you can't convert a tensor that has detached that has a gradient into a numpy, right? Touch will not let you. It will rather ask you or force you to detach that. So you can only convert a touch tensor that doesn't have a gradient, right, into a numpy. If not, you have to detach it first. So the other thing is you can also disable gradient tracking for neural networks where you want to do what we call fine tuning, right? Where you want to train, maybe you have a pre-trained network, right? You take that network is trained. Remember the knowledge of a neural network is in the parameters. These parameters we are talking about, the W's and the B's, right? And I want to now maybe I want to fine tune this network to maybe a network that was trained to recognize, um, you know, characters in a particular language, maybe handwritten characters in a particular language. But you now want to train it to recognize additional, maybe in your own language, there are some additional characters that that neural network wasn't trained on. You now want to fine tune that one because you don't want to start from scratch, right? Typically, when you are training when you are doing fine tuning, you're training this network, you don't want to alter the gradients of those ones that have already been trained, right? Maybe the body of the net, because that took a lot. Maybe it took how much, you don't know how much compute, how many months it took to train that network. So what you want to do is you want to only train the small additional piece of additional layers that you have added, right? Maybe let's say a neural network that has maybe 10 layers or 20 layers, right? And you now add 2 layers just to fine tune with the 2 layers to do additional stuff that you want it to train it on. If you do not lock the weights, the parameters in those 20 layers, right? When you are training the 2 layers, you are going to corrupt that network because those remaining 20 layers will still get their parameters updated when Touch is doing the autograd, the backward. So in that situation, what you do is you can disable gradient tracking or freeze the parameters. That's what they call freezing. So you can mark as frozen or, mark those parameters as frozen or something, right? We'll see how to do that when we get to training and fine tuning. We're going to talk about fine tuning later. But what that basically means is that you are going to essentially mark all the parameters in those 20 layers as not requiring any training. Requires grad, right? Not requiring gradients. You said it requires grad to false. Then the 2 layers that you want to train, you can then set requires grad to be true. Okay. And that helps to kind of train only the part that you want. So that's an interesting thing, right? So there are many different ways for that. So the other thing I just want to mention is AutoGrad keeps a record of the tensors, or data that is the tensors themselves. The data is always held in tensors. Executed operations, including the functions and all of that, along with the resulting new tensors in what we call a DAG. A DAG is a directed acyclic graph. This thing that you are seeing here, that's the technical name for this thing. It's a directed acyclic graph. A directed acyclic graph is a graph that has direction. So you can see the transfer of information only goes in this direction. That's why it's called directed. It always goes from the child to the parent, right? It's directed. It's directed. You don't have information going from the parent back to the child. Of course, when you are doing back propagation, it actually goes backward, but that is a different graph. In that different computational graph, you now have, it's still a directed acyclic graph, but this time the direction is from the loss backwards to, this backwards to the children and so on. So that's what directed means. The second thing, acyclic means the graph does not allow cycles. In other words, a cycle is when a you have a loop from parent to child and back to parent. So if, for example, we had this thing here, right? And we somehow allowed a return from the parent back. That would be what you would call cyclic, right? Cyclic is a graph where there is information that goes between child to parent and can also go back from the parent to child, right? That's a cyclic graph. But an acyclic graph is the one where this is not allowed. Information only flows in one direction. Okay, so that's what a DAG is. And so the computational graph in the PyTorch, is implemented as a DAG, right? And in, the DAG, the leaves are input tensors, right? Basically, leaves are the input that goes into the graph. Then the roots are the output tensors, which you can see here already. This is the root. The root is the parent that is at the tip, the parent that doesn't have a parent. Basically, a root is a node that doesn't have a parent. A leaf is a node that doesn't have a child. Okay. And in this case, remember it's directed, but the direction is from child to parent. So this is a parent that has two children. This parent also has a parent, and the parent of that parent also has two children, and it goes all the way. So this is like great, 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 great grandparent. It doesn't have any parent, so that's why it's a root. And then these ones that don't have any children, they are the beginning. They are leaves. So leaves are always inputs into the graph. So you can see the X is an input, the weight and biases are an input. The Y is also used to calculate the loss. It's also an input. So leaves are always inputs in a DAG, right? In this, the way that PyTorch is implementing it, right? And the roots are the output. So when you trace this from the roots to leaves, as you are tracing it backwards, okay, you can then automatically calculate the gradients using a chain rule. So remember, gradient is basically the gradient of each leaf is basically the the product of all the gradients. So the gradient of x is actually a product of gradient here times the gradient here times the gradient here times the gradient here times the gradient here. That's it, right? For example, we saw that the gradient of z is loss times the gradient of CE. We saw that, when I was doing an example, the gradient of the intermediate output, the z, is the loss, which the gradient of the loss itself, right, times the gradient of the activation function. Or in this case, okay, this is the gradient of the loss function, rather. If there was an activation function here, you also multiply that. So the gradient of the loss function for a binary cross entropy is um is y minus y hat. That's what it is, right? And then you can multiply by that. So just by chaining this, that's a chain rule, by chaining the gradients from the loss all the way back to x, right? And then from the loss up to this point and then down here to w, up to this point, then down here to b, you can now see, um, and then if we wanted to calculate gradient for y, but remember these ones, we are not calculating gradients for them. We're only calculating for these two. So that's why it will be the products across here and all the way down here. And that's it. So that's how that's just the looking under the hood, the internals of PyTorch, of AutoGrad, how it does a calculation. So by tracing the graph from roots to leaf, it automatically computes this. So in a forward pass, AutoGrad will do two things. First of all, it will run the recursive operation to compute the resulting tensor, while also maintaining the gradient function in the DAG. So whenever it calculates, whether it is a sum, as it is doing the function, it will find the gradient function of that function and you keep it, right? Still alongside with the tensor, inside the tensor. It actually stores in the same tensor. And that's what we saw here. That's why in these tensors, you see this gradient function property, which basically stores the gradient function counterpart of the function that was used to calculate this tensor, right? So it keeps that. And in the backward pass, when backward is called on the DAG, AutoGrad would then compute the gradient by taking the gradient function and applying the tensor as arguments into the gradient function, right? And then as it is doing that, it is accumulating the gradients. Each tensor will keep its own gradient in the grad attribute, right? And then when it is done, the chain rule will now propagate this grad and calculate it all the way back to the leaf nodes, right? So like we said, the graph is always recreated from scratch after each backward call. After each backward call, AutoGrad will basically clear the graph and start creating a new one. So what that does is, first of all, the benefit is allows you to use flow control. And then secondly, it allows you to change your computational graph, to change your model without, having to come back and recompile. Is what makes it just in time and all of that. So the other things you can read here, I'll leave that to you to go check it out when you have the time. Just go to automatic differentiation in the Python documentation, click on the Google Colab, and you can play around with it. So now, having looked at that, let us now quickly go to optimization, because optimization is like the key thing, right? You want to um, so we kind of already talked about optimization in already. Um, so we are going to understand this whole optimization thing. We're going to look at it in the context of the entire training loop, right? Remember a training loop we'll talk about that, but we'll look at training loop and where optimization comes in. Optimization is the last, more or less the last step in the training loop after the gradient calculation, which AutoGrad does, right? And then after the forward propagation. So we understand what we call loss landscape, and the problem optimization is not straightforward, right? The optimization has issues, and you need to understand some of those issues, and that will help you to decide which optimization algorithms to use, the pros and cons, there's no single one that solves all kinds of problems. So we're going to explore different optimizers from the grandfather of them all, the gradient descent, and then all the variants of gradient descent. And then we'll understand learning rates. We've already talked a bit about learning rates, but we'll understand a bit more. And then we'll look at what we call learning rate schedulers. And then we'll just build an intuition about optimization behavior. So like I said, training is really an optimization process, right? You have this training pipeline here. Step one, you do a forward pass, which is you pass the inputs into your model that you have already built, right? Your model does a prediction. That prediction is not exactly equal to your your true value, right? So because it is not your true value, you compute a loss. The loss is how far away the prediction is from your true value. So you basically do a loss computation, and you can use any of the different, you know, types of loss functions, right? You have binary cross entropy, like you said, categorical cross entropy, mean square error, and a whole bunch of others, right? But those are like the three most frequently used ones. Okay. When you've calculated the loss, the next thing is from that loss, you want to calculate the gradient, right? At that point, gradient of that loss. So when you calculate the gradient, you then back propagate the gradient like we just talked about now. Python does it with autograd. So for every parameter, you will calculate the gradient that corresponds to that parameter. For every parameter, you calculate the gradient. And like we saw, in most cases, the gradient is dependent upon the specific output. Each Y will kind of have gradient, and every weight that ties to the same Y or the same output will kind of have the same gradient. Okay. Then when you back propagate the gradients, every single parameter that you want to train will have the gradients. So what do you now do? You now take the values of those gradients and you update the parameter. You update the parameter. That's where the optimizer comes in. Okay. So training is basically navigating a loss landscape using gradients, right? So training is not really about training a neural network or any model for that matter. It's not about solving equation, right? If you wanted to solve equation, we would have used the normal method, right? You just find an equation that represents the entire solution to that entire complex neural network and we solve it. But we are not doing that. We are doing iteration, right? And it's iterative search. You are basically searching for the minima or the minimum, right? So whenever you are doing a search for either a maxima or a minima or a maximum or a minimum, it is an optimization problem. So the optimization problem is find the parameters of a model that will minimize the prediction error. That's what it is. This is what we have been doing since what we've been talking about, right? F theta where theta is a specific set of parameters, right? F theta x, that will give you the y hat, right? And you use L. L is a cost function. So L of y hat comma y is basically cost function that takes in the y hat, which is the predicted value, and the y, which is the actual value, right? And calculate the cost. And like we said, there are different ways of calculating the cost, right? Which I just mentioned. Then the minimum, you find the parameter that gives you the minimum cost. That's what argmin means. Min means the minimum cost, but arg means the argument that gives you the minimum cost, right? And the argument in this case is the parameter. So theta represents the parameters. They both weights and biases. So weights are W, biases are B. When you combine the two of them, you use theta to represent them. F theta of X represents the prediction of the model, which is Y hat. Y is a true label. And this function, this symbol, L, represents the loss function, which can be anything. We've mentioned 3 or 4 of them, and there are many others. So the common loss functions, of course, you can see them here. The mean square error, MSE, which is what we use for regression, linear regression, and other kinds of regression. Then the cross entropy loss, which is a classification, a binary classification. Cross entropy loss is used for classification. So you have binary cross entropy for binary classification. Then you have categorical cross entropy for a multi-category, a multi-class category classification. Then you have the negative log likelihood. Well, negative log likelihood is binary cross entropy basically, so it's the same thing. Okay, so there's this thing we call a loss surface. A loss surface would be if you were to take the loss, right, calculated from every possible combination of values of the parameter theta. Like for every set of parameters theta, right? You take a theta where x is a set of, sorry, where the weight, the x will be the constant, y will be constant, but the weights and the biases are a particular set of values, and you do a prediction and you plot that as a single data point. Then you take another set of weights and you plot another data point and you do that, right? By the time you plot that, lots and lots of them, you have this thing which we call a loss surface. So a loss surface is basically a mapping, like I said, from parameter space to loss value. What this means is what I just said, right? You take each set of parameters and then you plot the corresponding loss based on this set of parameters. You take another set of parameters, we plot it against another corresponding loss. So you do that for a million different sets of parameters or a million different combinations of parameters, right? And you now have x-axis and y-axis where x is the model parameters that you use, and y here we have it kind of represented in the three-dimensional, thing. But this is a two-dimensional version of it, right? Where theta is all possible combinations of the parameters, and then y is the j theta, which is the cost function. Okay, we'll come to talk about when we talk about convex and non-convex loss surface. So, but what we are saying here is that when this is how it looks, you can see how this thing looks like mountains and valleys, right? When we talk gradient descent, this is basically what gradient descent is, right? This is the loss surface in a two-dimensional plane, which we saw when we started gradient descent. So you start at somewhere here, maybe, and then you keep training and it keeps going down until it gets to the minimum point, right? This is in a two-dimensional case, right? Where you are just dealing with a single x value, right? Or x1 and x2, right? But when you have, this is real life, like somebody actually did a research on this and plotted all these graphs, and you see how this thing looks. You see that there are some places where it's very deep. This is the absolute minimum down here. This is where if you were able to do gradient descent and get your parameters to correspond to this point, this will be your best trained network because this is absolute minimum. But if you're up here, well, this is this is a worst network. But of course, you never be here. With gradient descent, you can drop. But there's something we call local minima and saddle points, right? Local minima is a minima, like this one. This is a minimum. This is a minimum. It's a minimum that is not the lowest. So if you were actually here in this place, you see that surrounding this place, you have places that are higher than this value, but this value is low. It's a minimum. So the model will perform very well, but it is not a global minimum. It doesn't perform the best, right? So you need to figure out a way to jump. Remember, gradient descent is always descending. It cannot climb up the slope. It's always descending down. So it cannot jump up. So you need to figure out a way to jump up and bring it down into this place here that will bring us down here, right? So this is just kind of a visualization to allow us to see when you're thinking of optimization, gradient descent, and so on, what we call the loss surface or the loss landscape. This is how it looks like. So one of the key properties is it's highly dimensional because the values of X that you push into a neural network has lots of values in it. So it's a multi-dimensional value, right? You see millions of dimensions. The other thing with the loss surface is that it's non-convex, and we're going to talk about what convex and non-convex means. But because it's non-convex, it has local minima and global minima. So that's the most important thing. It also has saddle points, right? And it has regions that are flat. So the loss surface is a difficult problem. That's why when we say optimization problem, this is what we're talking about. We're talking about a non-convex function that has so many different minima. And if you are not careful in selecting your hyperparameters, your model will settle in a local minima and it will not become very good. It will not learn the best, right? The best is the global minima. So there's no global map, right? And only local gradient information is available. So that's the thing with this optimization problem. There's no way for you to know, oh, this is the value I would take that will take me to the global minimum. Rather, I have to keep taking steps, based on the gradient calculation. So what is a non-convex function or non-convex loss surface? So first of all, a convex versus non-convex. A non-convex function, this is a convex function. This is a non-convex function. Now, you can see that what jumps out at you is that a convex function has a single minimum point, right? But a non-convex function can have multiple minimum points. So the mathematical definition of a non-convex function is a function where if you draw a line segment between any 2 points on its graph, it can go below the graph. So let me explain that. That definition can be a bit confusing, but let me see if I can explain it. So if you draw a line, like a single straight line, let's say you take 2 points, this point and the other point, on a convex function, right? I draw a line between any 2 points on it, okay? This line segment is above the graph. So it's not non-convex, it's convex. I can do again. I take another 2 points in this graph and I draw a line, a straight line to link these two, right? This straight line is still above the graph. It does not go below the graph. Even if I were to pick this point that is a minimum, right? It is always going to be above the graph. Same thing here, above the graph, above the graph. I cannot draw a line below this graph that cuts 2 points, right? I cannot draw a line that, starting from one point on this graph to another point that goes below this graph. It's always above. That's a convex function. But a non-convex function, you will find that there are certain lines you can draw. Like this one, I draw from here to here. It is above the graph, good. But I could also draw this line from here to here. And in this case, this line is below the graph. See where the graph is in this particular section, but the line is here. So for any function where you can draw a line between 2 points on that same function, and that line is below, right? Is below that, right? That is called a non-convex function. And you'll find that in real life, this is another example, right? In real life, Lord's surface is non-convex because the reason for non-convexness, if I may use that terminology, is because of what we call local minima, right, and global minima. If there was only a single global minima, then you cannot really draw that. If you look at it intuitively, you will see that. I could draw a line from here to here, right? Um, and in this case, where I draw this line from here to here, in this section here, let me just shade it a little bit. In this section here, shade. So in this section here is below the function. In this section here is also below the function. But in this section here is above the function, as you can see. So we have two sections that we have cut from this point to this point. Or we've cut through two sections that are below the graph, this and this, right? So this is what a non-convex function is. But the main significance of it, all I did here was give you mathematical definition. So next time, if you hear convex or non-convex function, you know what it means. But significance in machine learning, neural networks, in optimization is that there will be local minima, and there is always the possibility that your model can get stuck in this local minima if you do not pick your optimization algorithm. This is a local minima, this is a local minimum, rather, not local minimum, right? But this is a global minimum. This is where you want to be because this is the lowest point in your graph. But you can get stuck here. And the reason why you can get stuck here is because gradient descent always goes downwards. It doesn't climb up a curve. On this side, the gradient will be negative, so it will start going backwards and it will end up settling here. The only way you can leave this local minimum is if the step size is so big that it jumps out and then lands here, right? Then when it lands here, then the next step of gradient descent now take it here, but then it still gets stuck in a local minimum. So what does this mean? What this means is that normally, and we're going to talk about that. If you want to find a true global minimum, if you start with very small step sizes, very small learning rates, is the learning rate that determines your step size. Well, the gradient and the learning rate, right? If you start with really small learning rates, you might end up getting stuck in a local minimum. So it might not be a good idea. Rather, you start with large learning rates and it will land somewhere that is close to the global minimum. Then You now reduce the learning rates, and it can then use a lower learning rate to descend into the global minimum. So that's why you see that when we talk about learning rate scheduling, it's always a good idea to start with. You always start with a high learning rate, but there are other things, there are other problems with just starting with a high learning rate. So we'll talk about that when we get to scheduling. There's also a thing called saddle points, right? A saddle point is a point that is neither a minimum nor a maximum point. It's just a point where the gradient goes to zero and then increases again in the same direction. Because in a minimum, the gradient is negative and then it becomes positive, right? Negative and then it becomes positive. But here the gradient is positive, becomes zero, and then becomes positive. Here it was negative, became zero and went up positive. Negative, zero, positive. But here it's positive, zero, positive. So it's what we call an inflection point in mathematics, mathematics, or a saddle point. Saddle points can also be very difficult because when you're training a model and your optimizer can get stuck here and just stays here, right? It keeps going in another direction, other dimension. So anyway, optimization, the main thing I wanted to point out is this. Your optimization algorithm can get stuck in a local minimum, failing to find a true global minimum. It is something you need to be very careful about. So, and you cannot avoid this problem because that's the nature of the loss landscape, right? It is non-convex. So here are some additional, this is another view of it, right? This is a convex loss landscape in 3-dimensional. You can see it has a single minimum right here. But here is non-convex. You have a global minimum here. You have another local minimum here where you can drop in. And then you have these two maxima as well, right? So this is non-convex. So the key characteristics is in the shape is normally wavy. It has hills like this. It has valleys and potentially saddle points like this one, right? Where you have a gradient of zero, but it doesn't change direction, right? This one, it comes down and then it settles to gradient of zero and still comes down. It still continues to come down. Um, yeah, the minima, you can have multiple local minima, like we saw here, right? This one has like 1, 2, 3 local minima, right? And what makes a local minima a local minimum is that as long as you are training your model around this locality, it will always end up in this minimum. But this is not the global minimum. So your model is not going to become the best. It has not learned. Here is where it is the best possible it can be. And you always want it to be there. So that's non-convex loss. It can have multiple local minima and a single global minimum, which is the deepest deep, like here. So the main optimization challenge is that algorithms like gradient descent can easily get trapped in a local minimum, right? And you would mistake it for the best solution because it basically just plateaus at that local minimum, and it makes it difficult for you to find the global minimum where your model would have performed better if you train it to that point. So in machine learning, non-convex functions, which are particularly the loss functions in neural networks, are common. This is the main thing to know. The loss landscape is non-convex, and it can lead to complex optimization landscapes where training can result in different models depending on the starting point. And that's what we are saying. Like if, let's assume for this one, you are training your model and you started off around it and your learning rate is too small. I'm still again trying to point out the learning rate. So you can have a situation where you have low learning rate, you have 3 regimes, you actually have 3 models, but depending on where you optimize, or even 4 models, depending on where you initialize rather your parameters, the model starts learning from here, it will end up in this local minimum. Or especially if your learning rate is very low, so it cannot jump out. Or you start and you do a random, remember you're doing random initialization. You do a random initialization, and this time around your parameters get initialized randomly in here. It will settle to this second local minimum. Or this third one if your initialization starts from somewhere here, right? But you could also be lucky and your initialization starts from where the global minimum is. And in that case, yeah, it will get to the global minimum. But you also want a situation where, irrespective of where initialization starts, you want to still be able to get to this, right? So we'll look at the factors that you can do, the tweaks that you can do. Of course, one of them is learning rate scheduling, right? To make sure that your learning rates, you start with a high learning rate and you go down. So this is the key intuition around loss surface, and that's why I'm taking the time to look at that. Local minima are less problematic than saddle points in deep learning. That's one thing you need to know. Because saddle points, it's it's not even a minimum. It's like it's terrible. So it's even problematic. Flat regions will slow down your learning. So sometimes you introduce noise when you are using stochastic gradient descent. Noise is a way of basically randomly switching around the weights, but not all the weights. Like just randomly, you don't use gradient descent this time. You just use some random values to jump um the parameters around a bit, change it a bit, and see if you can jump from that focal point, like I showed here, of a local minima. Whether you can maybe I can jump if I switch the parameters a bit, I can jump it from here to maybe here, and it can start here, and hopefully it gets into a global minimum, right? When you train it. Okay, so let's now talk about the actual optimization algorithm. So we talk about gradient descent. Gradient descent is basically what we have seen. You iteratively minimize the function, right, by taking steps in the opposite direction of the function's gradient, right? Steepest descent. And we've seen that, so I'm not going to go through that. And use calculus to adjust the parameters. So basically, the gradient you calculate, like we've seen, you now go in the opposite direction to the gradient. That's why I use a negative sign. So you will see that here, gradient descent uses a negative sign. This negative sign basically means go in the opposite direction. This is a negative sign. Go in the opposite direction to the gradient. So you calculate the gradient. Remember this, the gradient is this function, for your information, right? This symbol, this upside down triangle is the uppercase delta character, right? Uppercase Greek alphabet, delta. So it just means the sum of all the gradients, right? Um, for this loss function, or the aggregate of all the gradients. So the gradient of the loss function, right? That is what you do. You take the gradient of the loss function and you multiply by nu. Nu is the learning rate. So the learning rate will determine how big of a step you take. That's why it's called the step size. So nu is the learning rate, and gradient is this is delta, right? This is delta, the um upside down triangle, right? And like we said, it's negative. You're taking a negative of the gradient. That is why you are changing the gradient by going in the opposite direction, use a negative value. So that will give you the new parameter, right? Theta t plus 1. Okay, theta t plus 1 is the previous parameter minus learning rate times the gradient for that particular parameter um, in that direction. And that's gradient descent. We've seen it already. So the benefits of gradient descent is you will have stable updates. It's always going to be stable. The direction of your parameter or of your model on the loss landscape is always going to be in the true gradient direction. But the cons, it's computationally expensive. So remember, let me say something. When we say gradient descent, we are talking about full batch gradient descent. That is, you are taking the gradient of every single data set or data point in the data set. So let's say you are training your model to predict, or you're training it on a data set that has 1 million data points. That means you are going to calculate the gradient of, and let's assume that you have a total 1 million parameters. So you're talking about 1 million parameters times 1 million data points. Okay, that's 1 billion. That's a lot for you to load into your memory at the same time and use it to update. So it's going to be slow and it's going to be memory intensive, right? Computationally intensive, because it's going to take a lot for you to calculate the gradient of everything at once, right? That's what gradient descent is, batch gradient descent. It is not scalable. It is nice when you're using it for small toy problems that has maybe like you want to train on 10 data points, like 10 rows, okay? Or 20 rows or 100 rows, or even 1,000 rows. It's all good, especially with GPUs. Yeah, you can train, but it's not scalable because for current large neural networks, deep neural network, the large language models that we're talking about, all kinds of things that have billions of parameters, it is not practical, it's not even possible for you to use gradient descent directly, the batch gradient descent, where you are calculating the gradient of all of them at once, right? You are calculating the loss of all of the data points, the total loss of all the data points, and then you're using to do a gradient. So, well, this is the algorithm, right? So, you compute loss on the entire data set. So this is the key thing, right? You're computing the loss on every single data point in the entire data set. Then you compute the gradients, right, for each parameter based on this loss that you've calculated for the entire data set, right? So take notes that, let me roll out some numbers. If you are, let's say you have a, a thousand or, yeah, let's say you have 1,000, um, data points, right? 1,000 rows. If you have 1,000 rows, then let's see, you have 1,000 rows, and you have maybe 1,000 parameters. Okay. Then your first computation is you are going to calculate. Okay, let me just make the numbers different. So you have 2,000 rows, and then you have 1,000 parameters. That is your your W's and B's, right, are 1,000. But your data points, your Y's, right, YI, Y to YN, Y1 to Y2000. There are 2,000 Y's, so there are 2,000 um, data points you want to train on, okay? So you calculate the loss. By the way, the Y could also be, we're assuming it's a single output that you want to predict, but the Y could also be 3. So if there are 3 Y's per um, network, then this will be 6,000 Ys, right? 3 times 2,000. So but there are 3,000 rows that you want to use to predict. So you first of all calculate the loss for these 2,000 rows, but it will give a single value, right? Because loss is always a single value for each Y, the loss will be a single value. So if you have 3 outputs, like a neural network that has 3 outputs, there will be 3 losses calculated. The loss for this one, the loss for this one, and the loss for this one, right? But that calculation of this 2,000 is computationally expensive. You now take this loss, you now calculate the gradients, and then you update the parameters. So this first part of the calculation is computationally expensive. And it is very slow because you are calculating the loss on a lot of numbers. So imagine these days we train neural networks on very, very large data sets. So this first part of the computation, because you're computing a lot of entire data set, is going to take a long time. So it's going to be slow. These other ones are more or less the same. These ones depend on the number of parameters in the model. The 2 and 3. Well, 4 is repeat. But the 1 depends on the number of data points. So this is the main reason why gradient descent is not used for real world training, because in real world training you really do have a lot of data that you're training on. So that's gradients. So the next one is stochastic gradient descent. So in stochastic gradient descent, what we now do is we take a single random data sample. We also have what we call mini batch gradient descent, which kind of has now been subsumed under stochastic gradient descent. So let's assume that you have a lot of values of not Y, of data points. So in stochastic, in the full batch gradient descent, which is the original gradient descent, you are going to pick the entire batch of 2,000, right, to train on. But in stochastic gradient descent, you are going to say, okay, let me take only 20 of these 2,000 and train. When I finish training the model with this 20, I'll now take another 20. I'll take another 20. And this second 20 I'll take should be different from the first 20, right? And then after that, I'll take another 20 again. And I keep doing that until I get the whole 2,000, which will take about 100 iterations. That is stochastic gradient descent. So the only difference, or the main difference between batch gradient descent and stochastic gradient descent, is that in batch gradient descent, you are calculating loss of all of the data points at once and using it to train the model, to calculate gradient and train the model. But in stochastic, you are doing in small mini batches or single items. In fact, there's a really the original stochastic gradient was you take a single item and train on one item at a time. But that also doesn't really make sense because that means I'll need to do this 2,000 times. So we now kind of arrive at a compromise and say, okay, we'll take what we call a mini batch, right? So a mini batch is just a small section of this and we use it to train. Then we take another section and do that. So that is stochastic gradient descent. So you use that instead of the entire data set, which is a traditional batch gradient descent. So stochastic gradient descent is really good for large data sets. Okay. So if you have data sets of 10 million, data points, your data, the rows that you're training is 10 million. It doesn't make sense for you to use batch gradient descent. You will now use stochastic gradient descent. And you are going to take maybe you can say, okay, let me split this into batches of 1,000, 1,000. So if I split into 1,000, 1,000, then 10 million, I can do it 10,000 iterations, right? Or 10,000, 10,000 mini batches, right? And I'll do 1,000 iterations. So this actually helps because it significantly reduces computation per step. In each step, imagine if I had to compute the loss of 10 million rows versus the loss of 10,000 rows, right? That is a huge, you know, difference. And this matters because when you're talking about when you're talking about computational power, we are looking at, okay, what can we do with current GPUs in today's world and so on, right? That becomes a key factor for you. What are the things, how can this GPU even compute, right? It could be so slow, but 10,000 would be much faster, and then you can parallelize things. So, but there is a downside to this, right? Because we are now selecting small sub batches of it, right? We are not getting the true loss of the entire data set. We are only getting a loss of a random sample of that data set or a selected sample of that data set. That loss of the sample is not necessarily equal to the loss of the entire data set. So when you do your training, okay, um, your your model will kind of have some noise because let's say you take the first 10 and you train, right? The first 10,000 you train, then your model is going in a particular direction based on the loss that is calculated for that 10,000. Then the next iteration, you take another different 10,000. This different 10,000 will have a different loss, which may be slightly different or even drastically different. And you continue training the model based on that. Then what will happen is that it will change direction. The way the model parameters, the updates, the gradients will be different. The updates will be different. So you start going in a slightly different direction. Then when you take the next 10,000 again, so you keep having some kind of randomness, right? And noisiness in the gradient descent. In fact, if you look at this, right, this is kind of depiction. Think about this as a lost landscape that you're looking at from the top view. Think about these circles. For those of us who did geography, right? You used to use circles like this to represent elevation, right? In geography. So let us consider that this is the global minimum. This is it, and this is up here. And each of these lines represents elevation lines, right? So gradient descent, we are basically just going this way until you get to that point. And in batch gradient descent, you go straight line because you're following a single direction. That direction is defined by the loss, okay? But when you now go and use stochastic, you can also go like this, right? But you still go in a straight line. But when you use stochastic gradient descent, see what's happening. You go up in this direction because this is the direction based on the first 10,000 samples. Then when you change and bring the next 10,000, it changes direction. And then you just keep going like that, like that, like that, like that. And that is how it is. So there's a sort of noisy behavior in the gradient descent itself. It's not straight, it keeps jumping around. But the interesting thing is that this jumping around is very good. Remember, we said that you can get stuck in a local minimum. You can get stuck in a local minimum if you did not, maybe if your random initialization kind of placed you around the local minimum, right? Place your model around the local minimum, and your learning rate is very small. It cannot escape that local minimum. So what will happen is it will just go into that local minimum, right? To go into that local minimum. But what stochastic gradient descent brings is that with this randomness, sometimes it can help you to jump out of a local minimum when you change the sample, the data subsample or the data sub batch or mini batch, right? It can then help you to jump out of a local minimum and begin to move and descend to towards maybe another local minimum, then jump out until it gets to a global minimum. So that's what we call it helps it to escape local minima, right? But it converges with more noise. So it's more noisy in the convergence. It's not a big problem, I guess. The noisy convergence is not really a big problem, right? So the notes for stochastic gradient descent is the implicit regularization is due to the noisiness. What we mean by regularization here is preventing regularization, we'll talk about it later, is a way of preventing your model from getting stuck in a local minimum by just changing things randomly a little bit. Okay, so it can jump out. So the truth of the matter is in the real world, okay, in real world training, SGD is the most commonly used optimization algorithm in deep learning, stochastic gradient descent. So again, this is a formula for it. It's the same as a batch gradient descent, except that you are calculating the loss for a mini batch, right? This batch here actually means a mini batch. You're calculating a loss for a mini batch, and you are changing parameters based on the loss of a mini batch, not the loss of the entire data set. Okay. So stochastic gradient descent is the gradient is noisy, right? Updates are more frequent, of course, because the sample size is smaller, right? So you actually will update faster. You also have faster iteration cycles simply because you are not doing as much computation as entire data set. Um, SGD works better because the noise helps to escape saddle points, in particular saddle points, right? Faster convergence, it actually converges faster in practice, especially in large data sets than the batch gradient descent. And it also leads to better generalization simply because it finds the beta minima. It comes really close to getting the global minima. So that's HGD, the second optimization algorithm. We'll look at the third one. So the third one is momentum, right? So momentum is basically stochastic gradient descent, but with momentum. So what is momentum? Momentum is just an additional factor that you add, and that factor accounts for the change in um the gradient, right, of the parameter. So it improves on the basic stochastic gradient descent by adding a velocity component, right? Or memory of past gradients. In other words, remember the values of past gradients. By remembering the value of past gradients, you are able to calculate the rate at which the gradients are changing, right? That is what we call velocity or momentum. Remember, momentum is basically mass times velocity. That's the physics definition of momentum. So we are adding a velocity component, right? What this does basically, it helps to ensure that if the um, gradient is moving too fast, it can slow it down a bit, right? To prevent oscillations. And if the gradient is moving too slow, it can speed it up a bit in order to improve or speed up um, convergence. So that's what it does. It helps to accelerate, um, in the direction where the gradient is consistently reducing the loss, right? It also helps to dampen oscillations and so on. So this was after people did all of this optimization. What I'm giving to you is the sequence historically, the sequence in which these things came up and how they were improved by researchers over time. So we started with gradient descent, then we did stochastic gradient descent. Now we added a momentum velocity factor just to um, help take note of that, right? So basically, it takes a weighted average of the current and previous gradients, allowing it to skip local minima and find better solutions more efficiently. So this is still trying to solve that optimization problem of a non-convex loss landscape where there are so many local minima. We don't want to get our training, our parameters stuck in a local minimum, right? We want it to be able to get to global minimum. So this is the problem with the plain old stochastic gradient descent. We talked about that. There's still a zigzag motion in the narrow valleys. There's a slow convergence in steep directions, and it's sensitive to noisy gradients. So we solve it with the momentum by adding faster convergence, right? Reduce oscillations and smoother updates. And how do we do that? We simply add this additional factor to the update. So the update, remember, if you look at this previous one, the update is minus nu, delta L, right? But here we take the nu delta L first. We add it to the velocity component. This is gamma, gamma VT1. So gamma is kind of a constant that determines how much of the momentum that will affect your gradient calculation. And then you take this gamma and you apply it to Vt minus 1. Vt minus 1 is the previous, is the velocity at the previous step. And remember, the velocity is calculated by the running average of the past gradients. You can see it here. Velocity is basically a running average of past gradients. And that running average is calculated by, it's not here, but it's basically, well, it's running average. It's a standard running average. The running average is normally take this one plus previous value times a certain factor, right? You reduce the previous value by a certain factor, reduce the previous value by a certain factor, and, add it to the current value of the gradient. Okay, and that gives you the velocity. You apply a gamma factor, the momentum coefficient, which is typically about 0.9, so that the momentum doesn't override it. And that's what you add to the gradient, the normally calculated gradient that we have seen before with the learning rate. And then that is what you now use to update the parameter, right? So that is stochastic gradient with momentum. Or sometimes in short, we call it just momentum, right? Then we now have root mean square propagation. This is another type of optimization algorithm, right? In the root mean square propagation, the main feature of it is that each parameter will have its own different learning rate, right? In previous things, stochastic gradient descent, momentum, we use the same learning rate for all the parameters. But what the RMS prop does, and by the way, RMS prop actually came before gradient descent, right, in history. But I put it here because I need it to explain the next one, which is the adaptive moment estimator, right, or estimation, the ADAM. We'll get to ADAM. But the RMS prop is an algorithm that allows to adjust the learning rate for each parameter individually. So, and the reason for this, you could say, oh, is this not the same thing as the momentum, where we're saying, okay, let's check the rate at which each parameter, the previous gradient, right? Previous gradient, and we use that as the velocity, we calculate velocity as the weighted average of previous gradient, and then we apply the gamma, right, to it, and then we use that gamma to add, right? So what's the difference between that and just an RMS prop? But the difference is it's kind of the same, right? The RMS prop was really popular in recurrent neural networks, which we'll talk about later on. But what it does is it takes moving average of the squared gradient. This is the main difference between RMS prop and momentum. Momentum takes moving average of the past gradients, a running average of the past gradients, while RMS prop takes the moving average, which is the same as running average, by the way, of the square of gradients. So the main difference is that you have moving average of gradients versus moving average of square gradients. But it not only does that, it uses it to do a standardization, a normalization of the current gradient. Remember, for those of you, when we're doing training of models, there's something called normalization, right? Where you can scale down the value of the input, right, by dividing it by the mean, okay, or dividing it by the range, you know, that is depending on how you want to look at it, mean or, range, standardization or normalization, okay? So that's what this does. RMS prop will take this, it squares the gradient, takes the moving average, uses that moving average to normalize the current gradient and scale it down before it then applies it to update the parameter. Okay. So um, what this does effectively is that um, the updates for parameters with large frequent gradients, okay, will get scaled down. While the updates, when I say updates, I'm talking about the parameter update. That is when you're doing theta equals theta minus, you know, the gradient. Because what happens is that when you normalize, right, the um, parameters that change a lot will have a higher value of this squared moving average of the gradient, of their own gradient, right? You will have a higher value, while parameters that don't get updated often will not have a higher value, be lower. So what will happen at the end of the day is that the parameters that have higher, more frequent updates will be scaled lower. So the value of that RMS prop component will be small. So, and that's what you will use to scale the gradient. So large, frequently changing parameters will reduce the rates at which they change, right? But small, rarely changing parameters will get larger updates. That's it. So it kind of balances it out. It tries to balance out so that at least there's no parameter that stays without getting updated. It kind of tries to do that. So that's what RMS prop is. And it works by computing gradient of the loss function. Okay. And it keeps an exponentially weighted running average of the squared gradients of each parameter, like I've said. Then it normalizes the current gradient by dividing by the square root of this moving average. So that's essentially a root mean square. Remember what we said, right? When you square things, you take the mean of those squared things. That's the mean square. Then when you take the square root of the mean square, you get a root mean square. That's why it's called root mean square propagation or RMS prop. So the value that you are going to use to divide the current gradient is the root mean square of previous gradients, basically. You are dividing or normalizing the current gradient by root mean square of previous gradients. So what that means effectively is that the learning rate for each parameter will depend on the previous gradient of that same parameter. So parameters with higher gradients will be scaled with a higher value. So the effective current gradient will be lower. But the parameters with lower gradients in the past will be scaled by a lower, root mean square of it. So the actual gradient that will be applied will be higher. So it kind of counteracts. And that's what we mean by saying that each of them ends up having a slightly different learning rate. So that's RMS prop. And you can see the function here. You have a loss function calculated on t, then the delta t, which is the gradient. So you just get a gradient. Then you can see this is the exponential moving average of the square gradient. So you have parameter here, which is phi, right? Phi means the decay, it's just a function to determine how much the effect of previous gradients will affect the current gradient. So you can see this is square of the current gradient, right? You add it to the previous gradient. Vt minus 1 is a previous, you can still see they use V, which is velocity, but it's actually a running average, right? So, and this is how you calculate running average, right? By taking the previous average multiplied by a scaling factor, right? And then you add it to the current gradient, right? The current value, and multiply by 1 minus that same factor. In this case, it's squared. So VT is the moving average of the squared gradients, basically the mean square of the gradient. That's VT, right? Then, of course, the phi is a decay rate, so typically 0.9. So when you want to now update the parameter, you would take the VT, right, and take the square root of it. So that's what makes it the root mean square. And you now apply the learning rate. The new is the learning rate. So you're actually updating it by learning rate divided by this. You're actually taking GT, which is the current gradient, right? You're dividing it by the square root of the running average of the gradient. So you're dividing GT by the square root of the root mean square of the gradient. This epsilon, remember, if you remember, you guys did this thing. There's a factor that you use to avoid division by zero. That's what epsilon is. It's just to avoid division by zero, because if not, you will now have problems. Anytime you do a division by something that could potentially become zero, you always have to put an epsilon to it. So that's what this is. Don't get confused by it. It's just, the main thing is that you're doing GT over square root of VT, right? Times N, which is the learning rate. And that gives you the update value. And you use that update value to update the current parameter to get the next parameter. And that is RMS prop, okay? So new learning rates and epsilon, a small constant for numerical stability, okay? These are the hyperparameters also, like we can see. We have the decay rate, right, which is the rate at which the previous gradients, square gradients, affect the current gradient. And that is 0.9 in most cases. Epsilon, like we said, is to avoid division by zero. And then the learning rate, N, which is 10 raised to the power minus 3. Typically, when you use RMS prop, you typically would like to have pretty low learning rate. 10 raised to the power minus 2, 10 raised to the power minus 3, and so on. Okay, so that's RMS prop. Now, the next one is Adam. So what is Adam? Adam now combines momentum and RMS prop. And we're going to see how it does that. So basically, Adam uses velocity or momentum to adjust. That's the first thing, to adapt the learning, the gradient. But it also uses RMS prop method of using moving average of the root mean square of the gradient to adjust biases and other weights. That's basically what Adam is. So it combines the best features of momentum and RMS prop. Momentum in this case refers to stochastic gradient descent with momentum, right? And RMS prop, which we just looked at, to efficiently find the best parameters by adapting learning rates for each parameter. So you can see that adapting learning rates for each parameter comes from RMS prop, and then correcting for early stage bias, making it robust for complex problems with noisy data. Okay, so Adam provides a sophisticated way to navigate the error landscape of a neural network. Adam is like one of the most sophisticated optimization algorithms for neural networks these days. Even though there are now new variants of Adam, you have the Adam W, which we'll talk about, and the N Adam as well, right? So it allows for faster, more reliable convergence by tracking both the average direction, which is the momentum, right? And the variance spread of gradients. So how does Adam work? So first of all, instead of using a fixed learning rate, Adam calculates individual rates for each parameter based on the same technique that I just showed now with RMS prop. So it speeds up learning for some parameters and slows down for others. So it uses two methods. The first is the momentum method, which is the first moment, like we said. It uses an exponentially decaying average of past gradients like momentum, except that unlike momentum that use a running average, okay, our SGD with momentum use a running average, but Adam uses an exponentially decaying average. So it's still a running average, but with exponential decay. Okay. So it uses that to accelerate in a consistent direction, preventing oscillation, because Remember, sometimes you can have oscillation in gradient descent where it goes back and forth, back and forth. And sometimes if the size is too much, it can even jump out and it can even diverge, right? If there is no global minimum or there's no other minimum to jump to. Okay. So oscillations is good to prevent oscillation because it means your model will converge faster, right? Instead of going back and forth. So that's the first moment. The second moment is the RMS prop, which it uses the again exponentially decaying average of the past squared gradient. So remember, the RMS prop uses the root mean square, but this doesn't use the mean. It doesn't use the um what do you call it? It doesn't use the arithmetic mean. It uses the exponential mean, the exponential decaying average, right? So it's still a kind of root mean square, right? Except that the mean is an exponential decaying mean or average of the past squared gradients. And it uses that to scale the learning rate, the same way we just said, helping to manage noisy gradients and different scales and allows each parameter to kind of change independently. Then it also does what we call a bias correction, where it can correct the initial bias in the moment estimates, which are close to zero at the start. So it ensures more stable updates early in training. So these are the equations for adaptive movement estimator. So like I said, first movement, you can see it uses a beta one. That's the function. Sorry, that's the constant. Then you see MC minus one is the previous moment, which is the previous exponentially decaying average, right? And then it does one minus beta one times GT, where GT is the gradient of the current um, iteration, okay? And then that will give you the moment of the current iteration, which is the first moment. Then you calculate the second moment, which is the variance, basically. And you can see variance is the mean square, right? Square of means is what we call variance. Standard deviation is the square root of variance, which is the root mean square. So this is something that people don't remember, but that's why it's called variance. So you square the gradient, right? And then you do a weighted sum again, right? 1 minus beta 2. So beta 2 is now the factor, the scaling factor for the second moment, which is the variance, which is the part that does the adaptive learning rate. And so you get beta 2 is times VT minus 1. Same, this is basically the equation for running average or moving average. So this gives us two values. The first moment, which is the mean, MT, which is the mean of the gradients, and then the second one, which is variance, which is square of the running average or the exponential decaying average of the gradients. The exponential exponential decaying average of the square of the gradient. That's V2. That's why it's called variance. That is now, then the third thing that's done is the bias correction. We now do a correction for bias, right? By just applying 1 minus beta 1 of the current iteration on the mean and also on the variance. So you get a correction for bias, right? And it is this mean and variance that you will now use to calculate the update. So the update is now the mean divided by the square root of the variance. Simple. Okay. Remember, just like RMS prop, you need to take the square root because you squared the gradient. So you have to take a square root. And the epsilon is just there to avoid division by zero. And that is multiplied by learning rate. And you use that to update the parameter. That is Adam. So you can see that the hyperparameters for Adam are 0.9, which is beta 1, which is the first moment, and 0.999, which is the second one, right? What beta 1 0.9 value means is that there's a lot of um, the current gradient really doesn't have a lot to contribute. 0.999 means the current gradient has even far less to contribute because 1 minus 0.999 is 0.0001, right? So it really contributes a little. So that's it. Then epsilon, which is of course to avoid the division by zero. So that's Adam. And the advantages are it's computationally efficient with low memory requirements because the updates are very few. It's kind of targets and updates parameters that really matter. It handles noisy, sparse gradients and non-stationary objectives very well. And the hyperparameters are intuitive and they don't require a lot of tuning. Okay. So If gradient descent was just rolling down a steep slope, right? Adam would be a smarter hiker that you don't just roll down a steep slope. You actually choose, you step on the slope, and if it is steeper, you slow down, right? If it is not so steep, you change direction and so on. So think about Adam as an algorithm that is very smart. It also remembers the general downhill direction and adjust its stride size based on how steep or erratic the path has been. So it kind of has historical knowledge of how that slope has been. So we are going to go into the last one. Well, differences between Adam and stochastic gradient descent. Um, I'm just going to finish this very quick. So Adam has fast initial learning rates. It learns fast, but it also kind of knows when to slow down. HGD is slower but steadier. One other thing is that with HGD, you need to remember to adjust your learning rate. It doesn't automatically adjust learning rate. So that's the thing. Adam may converge to sharp minima, right? In terms of generalization, but HGD often finds flatter minima. So one thing you need to see here is that optimizer choice is problem dependent. There's no optimizer that is better or worse, or that is the best for every type of problem. The optimizer you choose to use depends on the type of um, network you are training, the neural network you are training, but it also depends on um, the kind of data set that you are training on. Okay. So many large-scale systems that you can see start with Adam and then switch to HGT at a lower learning rate. We'll talk about that. So we now have the Adam W and weight decay. So the difference is that the W means weight decay. So you now have weight decay that is decoupled from the gradient update. You can now see that the optimizers are getting more and more complex, more and more complicated. Um, and thank God we don't have to be doing it ourselves. All of what I'm doing here is really just to um, give us kind of theoretical background. So, at least you remember something. Okay. So the Adam W is the advanced version of Adam. It fixes the generalization problem that Adam has. Adam has a generalization problem, and Adam W fixes it by decoupling the weight decay from the gradient update. So when we get to talking about regularization, which we might do next week, we'll see what this really means. Regularization, like I say, is a way that you can make the weights kind of jump around so that they can jump out of local minima. But it's also a way of training weights so that it does not overfit on specific types of on the specific inputs that you are training it on, right? Or specific values, outputs, both input and output you're training it on, right? So there's a flaw in Adam. I'm not going to go into details on this one, but there's a flaw in Adam where the weight decay is coupled into um, the whole updates equation, updates formula, right? So what we do with Adam W is to decouple that so that it leads to better performance, okay? Especially in complex models and fine-tuning tasks by preventing overfitting. So Adam typically applies a weight decay, what we call L2, layer 2 or level 2 regularization directly within the gradient update step, which can interfere with the adaptive learning rates and hot generalization. So Adam W solves this by decoupling the weight decay and applying it after the gradient update. So you only do regularization after gradient update instead of before, and treats it as a separate step. So this separation allows the weight decay to work more effectively and prevent it from being scaled down, because typically that's what will happen if you do it along with the update due to the learning rate. The learning rate always scales down the impact of gradients. And that's it, right? This is the function, this is the equation for it. The only thing that we see here is that um, we decouple out the weight decay using the lambda theta t. So lambda is um, the the constant that determines the weight decay basically, but everything else is the same, right? The Yeah, everything else is the same as what we have with Adam. The key benefit, you have more consistent weight decay, you have better generalization, you have stable training at scale, And you can see that Adam W is a, well, I don't know what I should call it, Adam Wu or Adam W. Adam Wu. Well, okay. So modern neural network, deep learning training and frameworks use the Adam W a lot, right? Transformers, vision models, large language models, LLMs, which we are going there. We are slowly going there. There's another one we call NADAM, right? NADAM, but I'm not going to go into that. You see NADAM here. There are a whole lot of them. You can see we have gradient descent, batch gradient descent, which we talked about, stochastic gradient descent, which is mini batch noisy updates, SGD with momentum, which we now have velocity based updates. We have a Nesterov. So Nesterov has a look ahead. We didn't touch this, but you can see we have AdaGrad, which is another kind of optimizer algorithm. We have RMS prop, which we talked about. We have Adam, we have Nadam, which is Adam with Nesterov momentum, right? And then we have Adam W with Adam with decouple weight decay. So you can see some of them. The ones that use momentum, of course, HGD momentum using momentum. Remember, momentum is where you are checking also the rate at which gradients are changing by looking at the moving average. So you have a HGD normal momentum, then you have the Nesterov momentum, which is a different algorithm for calculating the momentum, right? AdaGrad RMS prop don't use momentum. Adam, Nadam, and Adam W use momentum because they inherit it from both the SGD momentum as well as from the SGD momentum. Adaptive learning rate, anyone that uses the RMS prop will have adaptive learning rate. So AdaGrad also has adaptive learning rate. RMS prop, then all the Adams have adaptive learning rate because they inherited it from RMS prop. Then weight decay handling, gradient descent doesn't even do any weight decay handling. All the other ones are manual. AdaGrad RMS prop are implicit. Adam and Nadam are poorly because the weight decay is embedded inside the object, the gradient object, so it's not as effective. But Adam W, they decouple it and take it out. Convergence speed, so you can see that the ones that have weight decay, and the ones that have momentum, rather, the ones that have momentum will converge really fast, right? And the ones that also have adaptive learning rate will converge fast, right? Undergrad also converge fast initially. The rates are really slow. The gradient descent is really slow because of the computational cost. HGD is slow because it is bouncing around on the loss landscape. HGD momentum improves a bit more because momentum kind of smooths out that bouncing around. And then Nesterov is a better momentum, which is a bit fast. Generalization, very good for SGD and Nesterov, and very high for Adam. Typical use cases, you can also see where you use them. Transformers, modern deep learning use Adam W, right? Nadam, noisy and unstable gradients. So you can see that if you are using it for educational purpose, toy problems, that's where we use gradient descent, like what we have been doing. If you want to train models with large data sets, you use stochastic gradient descent. But for modern neural network architectures, transformers, and so on, use the Adam with decouple with decay. So this is the summary of optimizers, right? And you can see the evolution of it. It started basically as gradient descent, focus on stability, stochastic gradient descent, speed and noise, momentum, direction, improved convergence, adaptivity, basically um, um, variable learning rates, depending on the what do you call it, the parameters, and then better generalization. So this is it. If you want to do exploring a prototype, use Adam. Large modern models use Adam W. Base final generalization, SGD momentum. Noisy gradients, use RMS prop or NADAM. Learning rate matters. So at the end of the day, even though we've spent a lot of time talking about optimization or optimizers, the most important thing is your learning rate really matters at the end of the day. If you pick a learning rate that is too high, you don't ever converge and you don't really learn. If you pick a learning rate that is too low, you get stuck in a local minimum and you never really get the best from your model. So picking learning rate is very important. Each of the optimizers have a different learning rate that you choose. You cannot just choose 0.01 for all optimizers. For example, you could use 0.01 for SGD, right? Like you can see here. But when you are using Adam, you have to go lower. If you use 0.01 for Adam, you basically just blow up, right? So you go for a lower one, 0.001, or even 0.0001. Again, depending on the size of your gradients. So those are some of the things you look at. And that's it, right? Adam and Adam without weight decay, the couple are not the same, right? The weight decay is critical and actually, you know, affects, how your models converge. HGD generalizes better, Adam converges faster, and noise in HGD helps find flatter minima. That's why it generalizes better because it's able to find, it's HGD is much better at finding the global minima, right? And that you could find a minima that is really close to the global minima. So you could say, okay, it's almost the same performance, right? But not the same. So that's it. Now, the modern way is with Adam, you have what we call warm up and learning rate scheduling. Um, Let me just quickly run through this learning rate scheduling. Learning rate scheduling is basically a way of using multiple different learning rates in a sequence, in a schedule. So you don't use a single learning rate because a high learning rate, like I say, is good at the beginning of training when you want to find the general area where your global minimum is. But you need to reduce the learning rate if you want the model to get better and better. If your learning rate is too large, it will not settle on the global minimum because the the um the loss landscape where the global minimum is might be too narrow, and your large learning rate is making it jump over that hole, jumping over it. It's not able to jump into it simply because the learning rate is too high. So um, again, learning rate determines speed of convergence, very important. It also determines the stability of training, and it also strongly affects your final model quality, right? You can have a good optimizer, but if you choose a wrong or bad learning rate, it will fail. So it is very important. This is the most important hyperparameter in training neural networks. A good optimizer with a bad learning rate will fail. Let me say it again. Learning rate tuning often gives bigger gains rather than just changing architecture. If you could actually say, oh, I just did train a model and I cannot learn. But the problem was your learning rate. So you need to be very careful. Most training failures are learning rate problems. It's either too large or too small. Okay. The visual intuition, if you look at this graph here, this is a very high learning rate. You can see it's jumping around. It's not able to land in this because the um, update is too large for it to get. And when it hits here, the update, it goes in the opposite direction, but again, the update is too much. So it gets here. And you find that instead of going down towards the minimum here, it is jumping upwards and it will jump out. And if there's no other minimum for it to jump into, it will basically just diverge. So you find that your model never diverges. And I'm sure we've seen it. If your learning rate is also too low, you find that it changes too slow and it will take a long time to eventually converge. So you see the number of iterations here, 1, 2, 3, or probably up to 20, right? That's what a small learning rate, does for you. If it's too small, it requires too many updates before reaching the minimum point. But if you pick just the right value for your learning rate, then you find that 1, 2, 3, 4 steps, and you've gotten to the optimal point, right? The minimum. And optimal learning rate will get you swiftly there. So small learning rate will take tiny cautious steps. Large learning rate will jump over minimal. So take note of this. Um, Again, I've said it, if it's too small, you have slow learning, you get stuck in plateaus because plateaus are where, the gradient becomes zero or very close to zero. So you basically will not escape out of that plateau and it wastes compute because you keep computing, you keep cycling, but you are not getting better. Your loss is not getting better. But on the other hand, if your learning rate is too large, it oscillates like you're seeing here, right? And the training diverges and the model will never converge. So one of the things that we do to solve this learning rate issue is what we call learning rate schedulers. A learning rate scheduler basically is an algorithm that will dynamically adjust the learning rate that you are applying to train the neural network over the course of the training. So you don't manually adjust the learning rate. You typically start with a high value of the learning rate so that it will quickly learn fast, get to the general area where you have the global minimum, right, in that loss landscape. And then you gradually decrease the learning rate over time as it gets better and better so that it finds its way into those small, small holes and sections where in the loss landscape where you have the global minimum. Okay. So it prevents overshooting the minimum and leads to better, faster convergence and efficiency, right? Um, Different training phases need different learning rates. Like I said, the early phase of training is exploration. Find the general area where you have low loss, right? And then the late is refinement, where you now in that general area go lower, go deeper to find a really good you know, um minimum. So again, I don't think I need to repeat this, but the same thing. It's not a good idea to use a constant learning rate when you're doing training of an actual real world model, okay? Especially deep neural networks. The high learning rate early will help escape bad region. The lower learning rate will keep in minimal. If you keep it at a very high learning rate all through, yes, it will get to the general area of the global minimum, but you never achieve that global minimum. And if you also keep a very low learning rate, it may never get to that area of global minimum. It may get stuck in a local minimum. So that's the thing. So a scheduler would basically do this. And there are different kinds of schedulers, right? You have a time-based decay, you have a step-based decay, you have an exponential decay, and you have a linear decay. So learning rate schedulers will give you better convergence, avoid pollution, avoid oscillation, and it will prevent the model, from basically bouncing around. It improves the performance. Improved performance means your training is faster, right? But it also means that your model gets to a very good point in the loss landscape, so you have better accuracy, right? So generally, the learning rate scheduler, you will give it a starting point. You tell it where to start. It begins, and it's typically a very high learning rate so that you get a quick initial weight update. And then after a set number of epochs, the scheduler will reduce the learning rate and then train with the new learning rate. After another set of epochs, it will reduce again. And you keep doing that, depending on the algorithm that you use to determine how the learning rate should be reduced. So typically, you are going to see a learning rate scheduler as basically training using multiple learning rate regimes. So the step decays is one where you just reduce the learning rate by a certain factor, maybe say times 10 or divided by 10. So that means if you start with 0.01, after 10, after maybe whatever number of epochs, n epochs, 100 epochs, 1,000 epochs, it will now reduce the learning rate by 10 to 0.001 automatically and continue training with that. After another 1,000 epochs, it will reduce again by 10 to 0.0001, right? That's step decay. So you just, by steps. Then exponential decay is you decrease the learning rate exponentially over time, right? And exponentially you use an exponential equation to calculate. So it's not just a straight up division, which is what step decay is. Then we have what we call a cosine annealing. So cosine annealing follows a cosine curve, right? And a cosine curve starts with 1 and it follows a sinusoidal waveform. It goes down to 0, it goes down to negative, it comes back up to 0 and goes back up to positive, right? So basically you modulate the learning rate with that cosine curve. That's what cosine annealing does. So it reduces the rate and sometimes restarts it. Even though in training, you don't actually get to the negative parts of the cosine curve because that would just be a negative learning rate, which doesn't make any sense. So it's really a positive part of the cosine curve that it uses. Then you have reduced learning rate on plateau. This is an algorithm that says when the model has flattened out, plateaued, the loss doesn't change anymore. In other words, the the difference between the current loss and the last loss is certain value, right? There are some of you in your submissions, I saw you doing something like stop training on that kind of condition. But the best thing you would have done is not to stop training, but reduce the learning rate. So when you get to a point where the cost plateaus, you then lower the learning rate and see if the model will learn some more. So the metric that you can use to determine could be validation loss or any other kind of loss. Then you have a cyclic or one cycle learning rate, where you cycle the learning rate up and down, right? You basically increase it and then you bring it down, and then you increase it again and bring it down. So um, then you have more advanced ones. We've talked about step decay. So that one, like we said, the new learning rate is the original learning rate times a factor, which is the factor is gamma, which could be 10 divided by 10 that's times 0.1 and so on. There's also something we call warm up. Warm up is a situation where in some cases when you're training neural networks, you don't want to start with a very high learning rate because that will degrade the neural network, especially if you're doing fine tuning. A neural network has already been trained, right? If you start with a very large, high learning rate, you will just destabilize training and damage the model. So in that case, we do what we call warm up. So warm up is where you begin from zero and you ramp up the learning rate gradually, following a linear, curve until you get to the starting learning rate you want to start with, right? The high learning rate you want to start with. And then you now apply other ones like the cosine and annealing and so on. So typically use warm up for transformers. Again, large language model, LLMs are basically transformers. When you hear GPT is basically um, generative pre-trained transformer. The T in GPT, as in chat GPT, that T means transformer. Okay. So you can use warm up for that. Large batch training, when you're training a large batch of data, and then pre-trained model fine-tuning, like I said, if you have a model that's been trained already, you want to fine-tune it. You don't want to start off with a high learning rate. You want to do warm up and just raise the learning rate from zero a bit so that the parameters will kind of adjust. Cosine annealing, I think I talked about that already. You just reduce learning rate following a cosine curve, right? And this is a equation for it. You see the cos pi t over t. This will result in a kind of cosine function. And that is what you do. You multiply that by the range, which is the maximum learning rate and the minimum learning rate by the not the range, the median, multiply by the median. So basically this cosine wave will be kind of centered around the median, the middle value of the range of learning rates, the start and the end. So cosine works, the cosine annealing works, it gives us smooth decay, it avoids abrupt drops, and it encourages better minima. So these are some of the examples. And in modern training, the best practice is you use the Adam with the couple weight decay as your optimizer. Then you do warm up, like we said, and then use cosine annealing for your smooth learning rate adjustments. And then you monitor validation loss, not just the training loss. So that is that on optimizer. What I would have loved to do, but I think we run out of time, is just to try out different optimizers and see how they work. So um, I'm going to share a notebook that allows us to do that. Okay, so let's take a look at this. So here, right, what I just want to do is I'm just going to do this and then I'm going to share it. I have first of all just created this function. This function allows you to plot what we call a decision boundary. A decision boundary is a way to um, show how well your model is able um, to model the data you've given it and the training data and how well it can predict, right? I had already done something like that here. So this is an explosive OR problem. Unfortunately, we don't have enough time to touch this, so we will touch it when we come in next week to look at this. But the whole idea is this. Um, remember we did this last time where I built a simple net that I called an exclusive OR net, XOR net. And We train that XOR net on the exclusive OP problem. But unfortunately, I found that my model still could not solve it. It it kind of flattened out. It flattened out on um, a very low loss, but it still could not predict. Okay, still could not predict. So I want to try out different optimization algorithms just to show you how fast each of them converges. But we won't do it today. I'm going to share this notebook and then we'll do that next week. So that is today's class on optimizers and loss learning rate schedulers. Are there any questions? Okay, if there are no questions, we'll meet again next week. Let's have a great evening.